So looking at carbon and hydrogen, we've got the hydrogen orbital diagram and the carbon orbital diagram. And we see that carbon has two half-filled p orbitals, and hydrogen has a half-filled orbital. And so we could expect that hydrogen would overlap its orbital with one of carbon's orbitals, and that we could have another hydrogen overlap with the other one. And so that would look like this. And then the orbital, the p orbital that's not shown is this empty one. So that would predict that we would have a 90-degree bond angle, and that we would have a formula of CH2, that the carbon would bond with two hydrogens and call it good. But what we observe in reality is that this has a tetrahedral shape and a bond angle of 109.5, and the formula is CH4. So something is missing here. It wasn't too bad. It lined up pretty well for H2S, but it's not working for carbon. So what's missing here? The orbitals in a molecule aren't necessarily the same as the orbitals in an atom. So we talk about hybridization. So hybridization is when you take something and you modify it to make it slightly different, right? Or you take two things that are different and you bring them together and make a new thing out of them. Like, the dogs, the German Shepherd and the Golden Retriever, if they have puppies, those would be hybrids, right? A hybrid car can use gas or electricity, right? It can do both. So hybridization, we're referring to a mathematical procedure where we're combining atomic orbitals to make hybrid orbitals. And we are not going into the math. These hybrid orbitals are going to correspond more closely to the actual observed distribution of electrons. And they're still going to be localized on atoms, but their shapes and energies are going to be a bit different than the standard orbitals. What the hybrid orbitals do is they maximize the orbital overlap in a bond, and that minimizes the energy. When we hybridize these orbitals, we're going to get orbitals that are not symmetrical around the nucleus anymore. They're going to have more electron density on one side than the other. And so when they overlap, there's going to be a better overlap. Hybridization does require energy. It's not going to happen if it's not going to be used. And so what happens is forming those stronger bonds is a big enough payoff to make hybridizing the orbitals worth it. So what we're going to do is we're going to look at just hybridizing interior atoms, and we're going to assume that the terminal atoms are just regular. Okay? So general statements. The number of standard orbitals added together equals the number of hybrid orbitals. So in other words, orbitals are conserved. If you start out with 3 orbitals, you end up with 3 orbitals. They're just going to be different in shape and energy. Which combinations of those standard orbitals you hybridize will determine the shape and energy of the hybrid orbitals. And the kind of hybridization that happens is whatever gives the lowest energy. So doing a calculation like that to find out which one gives the lowest energy is way beyond the scope of this class. So what we're going to do is we're going to use Vesper theory to predict the hybridization so that we don't have to do all that crazy math. Okay, let's actually do it here. So here we're showing basically an energy diagram. So energy is higher, going up. We have, for carbon, we have the valence electrons. There are 2 electrons in the 2s, and there's 2 electrons in the 2p. And so if we think back to the hotel, so the 2 S and 2p, they're on the same floor of the hotel, but the P room costs more money to stay in, right? So the electrons are going to go to the cheap room first before they go into the more expensive room. What we're going to do here with hybridization is kind of like remodeling the hotel. So if we think of it this way, more horizontally, so here's our S room and our P room with 3 beds. What we're going to do is we're going to rearrange, remodel, and we're going to basically tear down the wall between them, and so now we're going to have 4 beds all in one room. So the 4 beds now all have the same cost, and the cost, the energy of that, is between the higher priced P room and the lower priced S room. Does that make sense? Little knots? Okay. We say these orbitals are degenerate, just meaning they have the same energy. So if we have these 4 orbitals now with all the same energy and we're putting 4 electrons in them, they'll each take their own orbital, right? Instead of pairing up. They don't pair up until they have to. So the result of this is now carbon has 4 half-filled orbitals that it can make bonds with instead of just 2. If we looked at the atomic orbitals, this is half-filled and that's half-filled, and those could make bonds. When we remodel this hotel, when we hybridize the orbitals, we get 4 orbitals that are at the same energy, and so we can have 1 electron in each of them. Each is half-filled, each can form a bond. Well, what's that going to look like? So essentially we're taking an s orbital, which is spherical, and 3 p orbitals, which are sort of shaped like dumbbells, and have these different orientations. And we're going to take those 4 shapes and essentially average them together. We're going to end up with 4 new shapes. And the new shapes are just going to they'll all be the same shape, but they'll be different in their spatial orientation. Just like these p orbitals have the same shape, they're just oriented differently in space. So combining all of these, the blue and the red makes purple. I like how they did that. What we get is sort of a dumbbell thing, but one lobe of this is much bigger than the other, and this one is small. And now these are 4 equivalent things, and just like the balloons in Vesper theory, they are going to be separated, spread out evenly in space, and they're going to form a tetrahedron. So each of these has its big lobe at one corner of that tetrahedron. When we put them all together, we get a shape like this. And what we're not showing in this picture is the little part of the orbital on the other side. This part is small and it's not significant for the bonding. This is the part that overlaps with another atom. So this is, like your appendix or something, and most of the time we ignore it. Right? So if we try to draw that in here, it gets really ugly, so we leave those guys out. So if we hybridize those orbitals, this new room in the hotel, we took the S room and the P room, and we took the wall down, we remodeled, and now it's one big room. And so it has the bed from the S room and 3 beds from the P room, and so this is called SP3 because it's an S and 3 Ps averaged together. They have equivalent energy. Carbon has 4 valence electrons, 1 in each. And so here are the purple hybrid orbitals. They're each going to have 1 electron. and then hydrogen comes in with its one electron in its half-filled orbital and overlaps and makes a bond. This lines up with experimental observations that carbon and hydrogen form the compound CH4, and that the shape of it is tetrahedral. Any questions? Yeah.
So even if that's like a balloon, the electron is just like, there's just two electrons in there, right?
So it's like this balloon with one electron and that balloon with one electron come, and they overlap. And now in this overlap, there's the two electrons that are paired up. And, you know, they look like balloons, but actually they're really more like standing waves. And so standing waves can overlap with each other, right? Whereas like solid objects can't. Yeah.
Would it be like a prefix to sp3, like for example, like 2p with 2 in front of it?
Yes, you could do that. So, you know, these, for carbon, these orbitals are in the n equals 2 principal level. And so you could refer to that as 2 sp3. We usually don't, but that's a reasonable thing to think because it was from the 2s and we had 2p orbitals, right? So those guys went together. Usually that prefix is left off though. Any other questions?
So, like, does that also imply that there's more electron density in the overlap?
There's more electron density in the overlap. Because, see, before, with the p orbitals, the electrons were distributed equally on both sides, right? And so now, you know, this larger lobe represents more electron density. And so there's more electron density on this side of the atom now. So that when this orbital overlaps with a hydrogen, say, it's going to be able to overlap better and be stronger. It's really important to at least kind of understand what I'm talking about right now because we're going to build on this. So if anybody is like, wait a minute, I have no idea what you're saying, I can say it again. So we're taking these orbitals, which hopefully you guys are all, it's like, oh, those kind of look like old friends now. We've talked about those. And we're going to average them together and make these new things. And then we're going to take these orbitals with one electron, overlap with another half-filled orbital so that we end up with a pair of electrons in there. What if we have a lone pair? So they don't draw the orbital diagram for this one. But so this would be our sp3 hybridized orbitals. And nitrogen has how many valence electrons? 5. So those would go 1, 2, 3, 4, 5. So one of these orbitals is going to have a pair of electrons just from nitrogen. That's a lone pair. So that's this guy right here. Typically put that one at the top. I don't know why. And then the other 3 orbitals are half-filled, and so they can overlap with hydrogen. So if we look at, hydrogens, over here's hydrogen. Hydrogen has an s orbital that's half-filled. That's this blue. So the half-filled orbital, the 1s on hydrogen, overlaps with the sp3 from nitrogen, which you could think of as a 2 sp3. So these 3 orbitals here are half-filled. Each of them can form a bond with one other atom. And again, this lines up with what we observe. This lone pair is going to affect the hybridization. So it will be a little bit, it won't be completely equal sp3. There's a little less p in here and a little more s. And so that's what's affecting the bond angles here. But we can just think about Vesper theory and think that this guy's more repulsive and he's pushing the other guys together. Any questions? So, how many sp3 hybrid orbitals result from the hybridization of one s and 3 p orbitals? So if we take one s orbital and 3 p orbitals, and we hybridize those together, how many orbitals are we going to end up with? 4. We start with 4 orbitals, we end up with 4 orbitals. So if you think about remodeling this floor in the hotel, we can take walls down, but the beds are not disappearing, right? Here, we started with 4 beds. There was 1 bed in the S room and 3 beds in the P room. We're going to take that wall down between the 2 rooms, make them one big room. Those 4 beds are still there. You have the same number of orbitals. So this is going to give us 4 orbitals. Yeah.
So that 3p orbitals, that's the 3 refers to the electrons, or
I should have just put P there. So this 3 tells me that there's 3 p orbitals. That we took all 3 of them. Because we're going to see in a minute that you can also take the s and just 2 of the p's, or the s and 1 of the p orbitals.
So when like this was pretty much discovered, they kind of used like conservation of energy to like justify it, basically. You know?
Well, I honestly don't know how they came up with this idea.
Because it kind of seems to follow it.
I like to think of conservation of orbitals.
Yeah.
You start with 4, you end with 4. So what if we take our 2s orbital and hybridize only 2 of the p orbitals and not all 3? These are supposed to be beds. I don't know if you're getting that or not. Kind of wonky. So this is the S room on this 2nd floor of the hotel. And there's 1 bed in there, 2 electrons, right? And right next door, because this is how rooms are, right? There's just a wall and then the other room is right next to it. Here's the P room, and it has 3 beds in 1 big room. So when we made the sp3 orbitals, what we did is we removed this wall. We took it down, and now we've got all 4 beds in the same room. Well, what if we don't want to do that? Well, we could move the wall, right? Take the wall from here and move it over here. Now we have this room that has an S bed and 2 P beds. And so this is sp2. And then we have left is a P orbital that is unchanged. And so that's this guy out here. So we take these 3 and merge them together, hybridize them. We're going to get 3 equivalent orbitals. And this one that wasn't averaged in there just stays the same. So taking the s orbital and 2 of the p orbitals, and now what we end up with, the shapes of these orbitals are still roughly the same, but these are 3 things arranging in space, and just like the balloons, they're going to make a triangle. So they're going to make this triangle, and that unhybridized orbital is sticking out of the screen and behind the screen. It's perpendicular to this. It wasn't affected. Any questions?
Can you say that again?
Can I say that again? Yes. So we've got the s orbital and 2 of the p orbitals, and we're going to hybridize them together. You know, we mix blue and red and we get purple, and so the shapes are kind of like this, but then that has an influence too. So we've got one big end and one small end. And these are going to spread around the nucleus to have as much space as they can, so they're going to make this trigonal planar shape. Well, what about the p orbital that we didn't hybridize? So this is on the x-axis, and this is on the y-axis. So the one that's missing is on the z-axis, which is coming out and going behind. So we've got this. It's going to kind of look like that trigonal bipyramid, except that these aren't electron groups, they're lobes of orbitals. And this and that is the same orbital. We'll skip ahead to this. So these are the hybrid orbitals. And this part up here and down here are 2 lobes of the same orbital. That's the p orbital that didn't get hybridized. And so it is perpendicular to these guys. So if we look at the orbital diagrams, and we're going to do H2CO, we've got hydrogen, we've got oxygen, and we've got carbon. Carbon is the central atom. We're only going to look at hybridizing the central atom. So hybridizing the central atom, this has sp2 hybrid orbitals from the shape we get from Vesper theory, and I'll show you how that works in a minute. So what we're going to do here is we're going to put these 3 together and call that sp2, and this one is left out. It's still there unchanged. And now, I think the biggest question you should have is, why did this guy go to the next room instead of sharing a bed over here? When we hybridize orbitals, the sp2 orbitals are closer in energy to the p than the s orbital was before. It's lower in energy, but it's a lot closer. And so it's like this guy, for 50 cents a night, it costs him more, but then he gets his own bed. So he's going to do that. And something very funny is happening out there. I don't know. But this sets us up for half-filled orbitals for 4 bonds. So what are we looking at here? These are the 3 sp2 orbitals. Each of carbons has 1 electron in it. So these are overlapping with hydrogen's half-filled orbital and hydrogen's half-filled orbital. This one is overlapping with oxygen's p orbital. See, what does oxygen have here? Oxygen has 2 p orbitals that are half-filled. So those can overlap. So here's one of oxygen's p orbitals. So that's going to overlap with this hybrid orbital. And another of its orbitals is straight up and down. This is half-filled, and this orbital over here is half-filled. And so the way these guys are going to overlap is they're going to overlap sideways. It's not as good. These guys are end to end. They overlap really nicely. This is kind of, they both have to sort of bend over towards the other one to overlap. So this kind of a bond where you have an end-to-end overlap of orbitals is called a sigma bond. Because if you look at that bond from one end, if you stand here and look down, you're just going to see a cylinder, round, right? Because this one is round and that one is round and they're lined up on each other. So sigma, the letter is round, right? So that's the end-to-end overlap. And then this type of overlap is called a pi bond. And I don't think this is why they call it that, but I think this is pretty funny. Turn your head to the left. Pi? Yeah. So there's pi. So this kind of makes a pi. Greek letter pi, not the apple pie kind. So here, this part and this part, it looks like that's two bonds, but it's just one bond. Question?
So, I'm very confused now.
That's okay.
So it makes the triangle shape, right? So would these ones,
Mm-hmm.
would it attach to that orbital on top?
So this red one, when we look at the P ones, there's I'm sorry, the purple ones, P purple. These guys have a second lobe, but it's small, and so we're ignoring it. These P orbitals, I'm going to get rid of that. So the original P orbitals were like this. And there's one electron, and it's in both sides, because electrons are weird that way, right? So this is like a standing wave where there's a node at the nucleus, and here's another one. And so these are trying to overlap, and so they're going to stretch and bend across. They're going to overlap up here and down here. That is one pi bond. The pi bond has these two legs, right? So that's one bond. It's one pair of electrons. There's an electron from this p orbital and from that p orbital, and they stretch over towards each other and they overlap just kind of barely. So that is a second bond. So this is a double bond then. Here's the first bond, and this thing is the second bond. That kind of makes sense? Yeah.
Does so the reason why the pi bond is kind of going around the sigma bond is because maybe the sigma bond has repels the other one, or how's that?
Yeah, so the valence shell electron pair repulsion theory, right? Electron pairs don't want to be close to each other, right? So here we have an electron pair. So we can't have these guys also being in the same space, right, as the other electron pair. But really the reason they're like this is because these p orbitals, they can't just change their orientation, right? This p orbital is the one that was lined up with the hybrid orbital to overlap end to end. This guy has to be perpendicular to that guy. This one here has to be perpendicular to the purple ones. And so it's like, well, why do they overlap at all? That's a very valid question. But they do. Yeah.
Another question. Can we imagine the whole thing as the Lewis structure too, with the Lewis structure, with help structure?
Sort of, yeah.
But if we do that, I found out that the oxygen, they have to
Mm-hmm.
and then they would have two lone pairs.
Right.
And
So this is not showing the lone pairs because it would get messy. So oxygen has 3 p orbitals, the red ones. So one this way, one that way, and one in and out of the screen. Right? The one that's going in and out of the screen has the lone pair in it. The other lone pair is the spherical s orbital. And if we try to draw all of those on top of each other, it gets harder to see. But if we look back here, here's oxygen. It has a full shell here, a full orbital here, so that's a lone pair. And this is a lone pair. And these are the 2 that are half filled. Those are the 2 that are going to participate in bonding. Which is why oxygen almost always makes 2 bonds. And this hybridization business is why carbon makes 4 bonds. Okay, any other questions?
that makes a lot of sense. Thank you.
Does that explain like why the bond length is less for double bond?
Yeah. So a double bond is shorter than a single bond, and it's stronger. So we have this bond pulling these 2 atoms together, and we have this other one, and that's going to pull them together more. So it's going to make it stronger, and it's going to pull them together and make the bond shorter. So what's really deceptive about this picture is it looks like there's 3, right? It looks like there's 3. There's 2. It's just that this one has the 2 legs of the one bond. So, yeah, just try to be okay with that. So, the sigma bond happens when you have the end of a half-filled orbital overlap with the end of another half-filled orbital. And so you can imagine looking down the center of this, and you're just going to see round redness. This is the side-to-side overlap. So these guys are parallel to each other, and so they're going to overlap to the side. So they're going to, stretch out and reach out over here. And that's not as good of an overlap. This pi bond is weaker than the sigma bond. We have these 2 bonds. The pi bond is weaker, the sigma bond is stronger. So as the bonds begin to break, the pi bond will break first, and the sigma bond would break after that. And, this is a single bond, one bond, and that pair of electrons is on both sides. I know it's troublesome. So this is the same thing. So here's the Lewis structure for this molecule that we're doing here. And so we see there's a double bond between the carbon and the oxygen. And so the double bond is this sigma bond plus the pi bond. And there's a single bond with the hydrogen and a single bond with the other hydrogen. And then there are the 2 lone pairs here that are not shown. We can label these bonds, and this is something the worksheet's going to ask you to do. So this bond, we're going to first identify the type of bond. That's a sigma bond. Yeah.
The orbital on the far right.
The orbital on this one. This is the other part of that orbital. Yeah, the p orbitals have a piece on each side. It kind of, yeah. And that's one of those things is, well, how can the electron be on both sides and yet never go through the nucleus? Well, because it's a wave. It's a wave and it's a particle at the same time. So we can label this as a sigma bond, and then we put a colon, and then the rest of the labeling is we're going to say which atoms is this between and what kinds of orbitals are overlapping. So this is the carbon with an sp2 orbital, so carbon, sp2, is overlapping with oxygen, and oxygen is using a p orbital. We can label the pi bond as well. So that would be pi colon. It's between carbon and oxygen, and both of them are using p orbitals. This will always be true of pi bonds. Pi bonds are made with p orbitals. They just are. We can also label these bonds. These are sigma bonds because it's the end of this hybrid orbital overlapping with the s. So sigma bond between the carbon is using an sp2 hybrid and is overlapping with hydrogen's s orbital. The labeling is on the worksheet. The labeling is not the big deal. So if you don't get the labeling, that's okay. So we have more insight here from valence bond theory than from the Lewis model. We see that double bond between carbon and oxygen is actually two kinds of bonds. It's not the same. Whenever you see a double bond in the Lewis model, it's always going to be one sigma and one pi bond in valence bond theory. The sigma bond is first, and then those unhybridized p orbitals are going to bend and stretch around it. The pi bonds are weaker because that side-to-side overlap is less efficient. It's not as good. The end-to-end overlap is better. So the pi bond in the double bond is easier to break than the sigma bond. Another thing that this explains is rotation. So I'm going to pull up my models. Somebody had too much fun with my model kit and build all kinds of weird things. I should have done this before class, but I had that long list of things I should do. Come on, get in there. I hope this is worth it. I'll be all set for tomorrow's lecture, though. You guys didn't realize you were the guinea pigs, did you? Okay. So I have made these two things. On the left here, we have two carbons. Those are the two black balls. And they each have two hydrogens on them and one chlorine. The chlorine is the green. A single bond, because it's an overlapping of end to end, you can get rotation. So this other chlorine, sometimes you might find it down here in the same area as this chlorine. Other times it might be up there. It can move around. Okay? This is this molecule over here where we have a carbon-carbon double bond. And so we have one hydrogen and one chlorine on each. But because that second bond, that pi bond is on the top and the bottom, it doesn't rotate because it's got two connections, right? so we can't rotate this one. It's like if you stick index fingers together, and you can rotate one hand, right? But if you put two fingers together, now you can't,
Finger tracking.
right? So valence bond theory is helping us to understand why single bonds can rotate and double bonds can't. A double bond is not just 4 electrons in a big thing, it's actually 2 pairs of electrons. Yeah,
Why would a single bond rotate?
because it can. Why would a single bond rotate? That's an excellent question. I don't mean to be silly. You'll actually see in some molecules a preference for one form over another. This one would probably prefer to be like this because the chlorines have more space. Chlorines are bigger than hydrogens. The balls aren't the same, but these are bulkier. And so if one chlorine is up and one chlorine is down, they have more space, but they can rotate around. So I think it's just basically entropy and randomness, and because they can. It's a great question, though. Yeah.
How do we know when this carbon will have semi-hydrogens like sp2 or when it has sp3?
I will show you that. I think that's coming up pretty soon.
Okay.
Yeah. Any other questions about this? So this is just looking at models similar to what I just made. So this one, there's free rotation, and so these chlorines can be opposite of each other or on the same side. When we have a double bond, we actually have 2 different compounds. They have the same chemical formula. But in one of them, both chlorines are on the same side of the double bond, and in the other compound, the chlorines are on opposite sides. And that's going to give that some different properties. They're going to react differently. Their boiling points could be different. So this is called cis, and that's called trans, because trans is across, right? The transatlantic railroad goes across all the way to the Atlantic. And cis, personally, I like my sister, right? So my sister and I are on the same side, if that helps you remember. But this is some stuff that you'll learn about in OChem, organic chemistry. So in section 10.10, we learned that double bonds are stronger and shorter than single bonds. We just talked about that. As an example, the carbon-carbon single bond has an average bond energy of 347 kilojoules, and a carbon-carbon double bond has an average bond energy of 611. Why is the double bond not twice as strong as the single bond? Think about the sigma bond and the pi bond. Are they the same strength?
Oh.
No. The pi bond is weaker. So you have the sigma bond, the 347, but when you add the pi bond, it's not a doubling of the energy, right? 611 is less than 2 times 347. That would be more like 700. So the choice here is this one. The double bond is actually 2 different bonds. They have different strengths. And so because the pi bond is not as strong as the sigma, a double bond is not twice as strong as a single bond. We can also have the S hybridized with just one p orbital. So, imagine the 2 hotel rooms. We're taking this wall down and we're just going to move it over a little bit. So now we have 2 beds in the first room and 2 beds in the second room. And this is going to be called an sp hybrid orbital because it's an s and a p. sp2 had 2 p's. sp3 had 3 p's. So averaging these two together, we're going to get 2 orbitals that look like this. And when we ignore this small lobe and draw them together, that looks a lot like a p orbital, doesn't it? But it's purple. That's a hybrid. Because red and blue, when you mix them together, makes purple, right? I hope they did that on purpose. This is one orbital, and that's another orbital. It's very easy to get that mixed up. Whereas this is one orbital, both sides are the same. So if we look at acetylene, it says draw the Lewis structure. Well, the Lewis structure is not much different than what it drew, what they show right there. There's no lone pairs. Acetylene has sp hybrid orbitals. So we take regular carbons, valence electrons, and we're going to make 2 separate rooms, each with 2 beds. And then the 4 electrons are spread out. So now we can still make 4 bonds. Isn't that pretty? Looks like a really cool pool toy, right? Anyway, so we have the sp hybrid orbitals. There's one on this side and one on that side. Here's another carbon. It has one on this side and one on that side. They're both half full. And so these two overlap end to end and make a sigma bond. So that one's labeled sigma CSP CSP. So each carbon is using one of its sp orbitals, the hybrid orbitals. The other sp hybrid orbital is sticking out in the opposite direction, and that's where the hydrogen overlaps. So hydrogen overlaps over here, and hydrogen overlaps over here on this carbon. And then we have 2 more orbitals. Those were the unhybridized p orbitals. Those are going to be perpendicular to this one. So we've got one up and down, and we've got one that's going in and out. Right? It has nothing to do with hamburgers. So this is a half-filled orbital, and this other carbon has one just like it. And so these can overlap side to side and make one pi bond. And the in and out orbitals can overlap side to side and make one pi bond. Now, if we think about VSEPR theory, and we're trying to figure out the shape of this molecule, we're counting electron groups, right? So this carbon has how many electron groups? 2. A triple bond is 1 group. And so 2 groups, like the 2 balloons, are going to be on opposite sides of each other, and that's these 2 hybrid orbitals. Questions?
That's pretty much like a tie bond sandwich.
Mm-hmm.
And the other one's like, I guess, a cracker.
Yeah, so we have 2 pi bonds, and so they're like surrounding the sigma bond, right? There's one top and bottom and one forward and back. It's like trapped or protected, depending on how you look at it. And there's this one in the middle. That one's stronger though. Yes? Could there ever be a sigma bond that would be like this? No. Because by definition, it's end-to-end overlap of orbitals. Now, this is a sigma bond that is outside of that mess, right? This is overlapping with hydrogen's s orbital. So this is a sigma bond, and that's a sigma bond, and this in the middle is a sigma bond. Okay? And then we've got these two up and downs are stretching over, try to hold on to each other. And then these guys are doing the same thing. And so we have 3 bonds. And that's what a triple bond is. What's the hybridization of carbon in CO2? Well, let's look at the Lewis structure. Any double bond is 1 sigma bond and 1 pi bond. Pi bonds are between p orbitals. Sigma bonds can be any kind of orbital. They can be unhybridized or they can be hybrid. So I need to have 1 sigma bond over here, and I need to have 1 sigma bond over there. So what am I going to hybridize to get 2? SP. So hybridizing them, I'm going to get an SP and then 2 unhybridized p orbitals. So the SP is going to be, on each side of the carbon. It's going to make a bond with oxygen. And then we're going to have this messy business with the second, I'm sorry, that was wrong. The carbon has a p orbital that it can overlap with this one, and then this p orbital is going to overlap with the other oxygen. And that just looks like I was scribbling. The answer is SP. So we looked at expanded octets in Lewis theory. And we said only elements in the 3rd period or larger can do this. In valence bond theory, this corresponds to hybridization that involves the d orbitals. So on the 3rd floor of the hotel, like for sulfur has electrons in the S room and the P room. It doesn't have any electrons in the D room, but the D room is still there, sitting there with 5 beds. Because just because no one's staying in a hotel room doesn't mean it disappears, right? Just because there's no electron in an orbital doesn't mean it doesn't exist. So the 3D orbitals are going to be similar in energy to the 3p and the 3s. They're on the same floor, after all, and so we can include those in our hybridization. We thought the other things were funny looking. So S, P, and D. Now in an atom like sulfur, those d orbitals are empty, right? Because we don't get any electrons in those d orbitals until after we fill up the 4s. So these are just all empty. But this molecule is saying, but I need 5 equivalent places to stay. I need 5 equivalent orbitals. So we're going to take 5 orbitals, an s and 3 p's and 1 d. And that's 5 orbitals. We're going to put them in the blender and pull them back out, and they're going to look like this, which looks an awful lot like trigonal bipyramid balloons, right? It's not a coincidence. So then we can have our electrons spreading out in here and forming up to 5 bonds. The other d orbitals, they're just going to sit there. So I'm going to draw my crazy hotel again. So this part is the D room, and this is S, and this is P. Drawing the beds takes too long. So there's a wall here, and there's a wall there. What we're doing here is we're going to tear down this wall, and we're going to move this wall over here. So now I have 1, 2, 3, 4, 5. I have 5 beds in the first room of the floor. And this other room, there's 4 empty beds, 4 empty orbitals. Those weren't changed. Any questions? Yeah.
Is that why the period P and below they can make more than an octet?
Mm-hmm. Yeah, this is exactly why things in period 2 cannot expand their octets. Because on the second floor of the hotel, there's an S room and a P room. There is no D room. So you can't expand into it. It can't happen. Your wheels are turning. Can you make a question?
No, I'm just like thinking, but like, so you get 5 d orbitals because it's one trying to make 5 sp3s, right? So is that how you get the 5 ds?
So it hasn't covered this yet. What we're going to do is we're going to look at the electron groups in the Lewis model. Count the electron groups. If you have 5 electron groups, that means you need 5 hybrid orbitals. So if we need 5 hybrid orbitals, we need 5 that are the same. You start with the S, you move into the P's, and if you need more, you pull in a D. Okay? And then these guys are just left over, literally left over. And so something with this sp3d hybridization, it has 5 orbitals arranged in this trigonal bipyramid shape. And if each of these overlaps with one atom, then we get those things that we were looking at on Monday. I think they go there. Yeah, like this. So here's arsenic, and arsenic is sp3d hybridized. So it's got 1, 2, 3, 4, 5 hybrid orbitals. And they're going to spread out away from each other in 3-dimensional space. And then each of these can overlap with an unhybridized p orbital on a fluorine. Isn't that cool? What I want to know is, why is this orange and not purple? So we look at the Lewis structure and see 5 groups. That tells me I need to hybridize 5 orbitals. You start with S, then you go into P's. I need all of those. I need one more, so I'm going to go into the D's. Come on. Well, what if you need 6? If you need 6, then you're going to grab 2 of those beds from the D room. You're going to move your wall over further, so now you've got 6 beds in one room. So this is called sp3d2 because it has an S and P3, there's 3 P's and 2 D's. And those 6 things, like the balloons, over there actually, are going to make an octahedron. Right? So now we can imagine each of these balloons as one hybrid orbital. That's what they were all along, but I didn't tell you. So something like SF6. Here's our Lewis structure. We look at the Lewis structure and we see there are 6 electron groups. I need 6 hybrid orbitals. S, P, 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 D, D. That makes 6. SP3, D2. Those 6 equivalent things now are going to spread out like this. Each of them has 1 electron. It can overlap with fluorine's p orbital that has 1 electron. Okay, so this is what I was getting at before. So how do we know which hybridization scheme best describes? Well, there's the rigorous method, which you can read about up there. Or there's the good enough for Chem 1A method. Since we're in Chem 1A, we'll go with good enough for Chem 1A. You assign the hybridization scheme from the electron geometry of the interior atom. Doesn't work 100% of the time, but we're not going to ask you about one that doesn't. So you look at the central atom and you see, well, how many electron groups are there? There's 2 electron groups. 1, 2. I need sp hybridization. There's 4 electron groups, sp, p, p, sp3. I haven't figured out how to grow 2 more fingers for the D's, but you get the idea, right? It's just however many electron groups you need, that's how many orbitals you need. You start with the S, you go through the P's. If you need more, you get into the D's, and you put them all together and hybridize them. So this is showing, we have these, different number of electron groups. The electron geometry, right? We looked at that from Vesper theory. The hybridization scheme, 2 electron groups, I need 2 orbitals. 3, I need 3. 6, I need 6. And they're going to have the same shape. So writing these hybridization and bonding schemes. Again, we're going to start with the Lewis structure. Yeah, question?
So back to the model, there
Mhm.
will never be a pi bond if it's the d orbitals.
Right, we won't get any pi bonds with the d orbitals because the unhybridized d orbitals are always going to be empty. They'll always be empty. Yeah, great question. Yeah.
Each orbital only has 1 electron or 2?
Well, each hybrid orbital can have 1 or 2. It depends. So if it has 2, then that's a lone pair. And if it's just all half filled, then they will all be single bonds.
So like, say for example, like, you know how you go S and G, P, and P's?
Mhm.
When you're filling those up, would you put 1 electron in each orbital, or would you put 2?
So when we hybridize them, these become degenerate, right? And so we're going to go across 1, 2, 3, 4, 5, and then we'll pair up if we need to. What's a little bit different is when you have like sp2, you know, here's your p, unhybridized p orbitals, and this is sp2. The energy gap here is really small, and so like carbon will spread out like that. But again, the Lewis structure is going to help us know what to do, because if you see a lone pair on the central atom, then you know that something has to be paired up somewhere, right? Any other questions? So you start with the Lewis structure. You're going to use Vesper theory to find the number of electron groups or the geometry. you're going to take that many orbitals and hybridize them. And then we sketch the molecule. You start with the interior atom and its orbitals, and then you show overlap with the orbitals of the terminal atoms. And you would label the bonds with the sigma or pi notation. And that is what you're going to do in that worksheet. And if you go to the assignment page for that worksheet, there is a video where you can watch me doing one of them. So you can follow along and know what all those different boxes are supposed to be. And if that doesn't make any sense, then you text me. Okay, so let's write a hybridization and bonding scheme for xenon tetrafluoride. And I'm going to go through this kind of quickly because we've got other things we need to do. So XeF4. So we start by making a skeleton, right? And then we're going to count up our valence electrons. We have 4 times 7 plus 8. So 4 times 7 is 28 plus 8 is 36. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Where do the rest of the electrons go? On the central atom. Lone pair, lone pair. 34, 36. So there's our Lewis structure. We look at the xenon, the central atom, and say, well, how many electron groups are there?
6.
There's 6. So I need to have sp3d2 hybridization. And that's the 6 balloons, right? So if I draw the hybridized orbitals, so I've got my sp3d2s, and then there's going to be 3 d orbitals that are just left out. So then I'm going to think about, well, xenon has 8 valence electrons, right? So let's put those in. 1, 2, 3, 4, 5, 6, 7, 8. The fact that I see 2 lone pairs on here keeps me from putting those 2 guys over in the D. We're never going to have those guys over there. So these are my lone pairs. And these are the 4 bonds. And they're going to overlap with the fluorine. And if we look at fluorines, fluorine has S and P, 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. It has 1 half-filled orbital. Fluorine almost always makes 1 bond because of this. So this orbital in fluorine can overlap with one of these. So drawing this, which, other than the worksheet, I'm not going to make you do this. So here's my xenon. I've got 6 balloons. Okay, so I've got one that's up and down. There's 2 of them. And then there's one going back and one coming out at me. And this one's coming out at me, and that one's kind of going back. Kind of get the idea? And each of those has an electron in it. But 2 of them have 2 electrons. So if I put a lone pair here, where did we learn that the other lone pair is going to go? It's going to go on the opposite side, right? So this is going to be a lone pair over here. So now I'm going to take fluorine, and I'm just going to draw the p orbital for fluorine because this is getting messy already. So here's fluorine, and one of its p orbitals has 1 electron in it. So those guys are going to overlap and form a bond. Here's another fluorine. P orbital. Another one. And another one. So these guys are in a plane that's perpendicular. They are like the blue balloons on my balloon animal thing here. The white ones are the lone pairs. So the bonding scheme, I'm going to describe the bonds. And these 4 bonds are all the same kind, right? They're between xenon and fluorine. They're all sigma bonds. So I can describe that as this is a sigma bond between xenon and fluorine. And what orbital is the fluorine using? A p orbital. And what is the xenon using? sp3d2. Got it in there somewhere. So this description applies to each of these 4 bonds. Yes?
What does the empty d orbital have to do with? That's like
These don't do anything. I like to draw the empty d orbitals over there because, I mean, we pulled in 2 of the d orbitals here, so we're showing some of them. Let's make sure we identify all of them because we should have the same number of orbitals after as before. But those were empty before, and they are still empty. They're not doing anything. They're just sitting there. But we took 2 of the beds and some of the space from that room so that we could fit all of these guys. Any other questions?
Is there like a trick to like figuring that out in case you forget like how many unhybrid like shortcut?
Well, it's not really a trick. Just think about, well, what did you have before? Let me do a different color here.
Because I was noticing it was going like odd and then even with like a pattern, but then it kind of just
So if we're looking at unhybridized, just regular atomic orbitals, there's S and there's P, there's 3 Ps, and there's 5 Ds. And yes, those are going odd numbers. 1, 3, 5. The next one would be 7. And that's because of the quantum numbers. I'm going to look at my number of electron groups to decide how many of these am I going to throw into the blender. Okay, so here we needed 6 because there were 6 groups. So 1, 2, 3, 4, 5, 6. So I'm going to take 6 of them. What happens to these? Nothing. They are still sitting there empty just like they were before. Okay? So on the worksheet, if you have d orbitals in your hybrid orbitals, I'd like to see the unhybridized ones just sitting there empty and minding their own business. Any questions? What's on the next slide? Write a hybridization and bonding scheme for HCN. Lewis structure. Let's just cut to the chase, shall we? There we go. That's the Lewis structure. How many electron groups on the carbon? So what hybridization do I need? SP. Right? So carbon had, these were its unhybridized orbitals, right? S and P. So if I'm going to do sp hybridization, I'm going to take 2 of these. And so I'm going to make the This is the sp hybrid orbitals. And then over here, I'm going to draw these just a little bit higher because they are higher in energy, but not very much. So these guys are there. And I have 4 electrons. So here is where looking at the Lewis structure will help you know what to do. Are there any lone pairs on that carbon? No. That means I'm not going to have any pairs here. So that 3rd electron is not going to go in here because that would make a lone pair. It's going to go over here. And we'll see that happen a lot with the p orbitals. We're not going to see it happen with the d orbitals, but the lone pairs will tell you not to do that. So for my carbon, here's my carbon. It has 2 sp orbitals. And those do what 2 balloons do. They'll be on opposite sides of each other. Right? So there's one over here. Actually, maybe I should stick to purple and red, because these are hybrid orbitals. One there and one here. And it also has 2 unhybridized p orbitals. One up and down, one in and out. Each of these orbitals has 1 electron in it. My electrons are going to be black. So hydrogen is going to be over here with its sad little single electron, and it's going to overlap with one of the hybrid orbitals. Well, what does nitrogen have going on? Now, we are not hybridizing anything except interior. So we don't have to worry about hybridizing this. We're just going to go with standard atomic orbitals. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. Just regular. This tells me that I'm going to form 5 bonds, and I'm going to have 1 lone pair. 5. That's 3. I can't count. It's going to form 3 bonds and 1 lone pair, and that's what my Lewis structure says too. 3 bonds and 1 lone pair on the nitrogen. So here's my nitrogen. I'm going to have to draw him a little closer. So there's my nitrogen. And he has an s orbital. Wait a minute. Oops, went too far. Okay, forgot what I was doing. Here's nitrogen. Nitrogen has an s orbital. The s orbital has a lone pair in it. You don't have to show that in your drawing. It makes things a little more difficult. And then it has 3 p orbitals. So 1 goes this way, and 1 goes this way, and 1 goes in and out. And each of those has 1 electron. So we get 1 electron from carbon, 1 from nitrogen in a sigma bond. And then we're going to have pi bonds. So these 2 and these 2. And so there's going to be a pair of electrons in that one and a pair of electrons in this one. It's really hard to draw. Yeah.
How do you explain this one? So how come on the sp p orbital you don't? It looks like the sp is a lower energy, so how come that doesn't get filled up? Like I know why, because you need 3 p orbitals to make the triple bond, but how come technically it doesn't fill up?
Right. So my best explanation for that is there's a price difference here, but it's like 50 cents a night at the hotel. 50 cents a night and I get to sleep in my own bed. Heck, that's worth it, even though I'm a cheapskate, right? The room itself is like $60. 50 cents a night is nothing in comparison. That's the best I got. So then if we're going to do the bonding scheme, we're going to describe these bonds. So let's describe this one first. What kind is that? Sigma or pi? That's a sigma. And that's between what two elements?
C and N.
Between carbon and nitrogen. And what orbital is carbon using?
It's the SP.
An sp. And what orbital is nitrogen using? P. So that's that one. There's another sigma bond here. What is that between? C and H. So that's between carbon and the hydrogen. What orbital is carbon using? sp. And what orbital is hydrogen using? S. Hydrogen always just uses S, that's all it's got. So the one hybrid orbital is making a sigma bond over here, the other hybrid orbital is making a sigma bond over there. And now we have two pi bonds. But they are equivalent, right? They're both between carbon and nitrogen. So there's this one, and then this one I made a little bit darker. So what kind of an orbital is carbon using? A p orbital. And what kind of an orbital is nitrogen using? A p. So we have one bond like this, and one bond like that, and two like this. Whenever you describe a pi bond, it's going to be p orbitals. P, pi, pi, p.
What will happen with that one? With the one that's on the right? On
The one that's over here?
Yeah.
Great question. So this is part of that orbital. All of this together is one orbital.
And there's only one electron, right?
Mm-hmm.
So we just ignore it.
Basically,
Oh.
yeah, we're basically going to ignore it. The overlap is going to come over here, right? This part isn't overlapping. That doesn't mean the electrons are never going to be over there, but they're not going to be there very often because they lower the energy of the molecule when they're between the nuclei. And so, showing these as unhybridized is kind of cheating because these orbitals are going to hybridize too, but we can understand what we need to understand without going there. So we're not going to go there. Any other questions? We don't want to do that.